All right, so we're going to carry on with our reviewing. Now we're awfully close to the end here. Right now we are in 4.4, which is our look at the fundamental theorem of calculus. And then 4.5, which follows it, is a look at, um, let me just go open it up for you. It is integration by substitution. Now, when that's done, then we can start chapter 7, which is where we actually begin the course for real. And that's where we'll see some interesting applications of integration. So in Calc 2, there'll be a lot of discussion about integration. You know, you were introduced to it in Calc 1, but here's where we really use it quite a bit of the time. So there's a lot of applications to go through, but right now we just want to wrap up our discussion about chapter 4, which is our review of integration. And so we'll go back and revisit now the fundamental theorem of calculus, which is really, it just ties together the concepts of differentiation and integration. So let's go back to 4.4. Oops. All right, so this is 4.4, yes, and they're introducing us. There's actually two, by the way, fundamental theorems of calculus. The first one is the one that we'll use most often. And they mention here that it was invented independently by Isaac Newton and Gottfried Leibniz, as is all of calculus, really. It was invented by them, apparently unknown to each other. Newton lived in England, of course, and Leibniz was German, and they had no way of knowing about each other. So, and they also, at least Newton was very secretive about his research. He didn't like to publish anything until he was really sure that it was ready, and that sometimes meant decades. So, historians since then have kind of tried to decide whether or not Newton was first or Leibniz. And I think the consensus seems to be that it was probably Newton, but just barely. And so again, it's it's not like now where everything that happens is available immediately on the internet. If there was a Newton and Leibniz alive today, they would see each other on the internet. They would see each other on social media, whatever. They would know about each other's research very, very quickly. They really did dislike each other though, because they both thought the other was trying to steal credit for their work. So quite a few books have actually been written about this. But anyway, so what they're doing here is this is the first, or sometimes it's simply called the fundamental theorem of calculus to distinguish it from the second one. And so what is this telling us? Let's copy this into the notes. And I think we're going to do some examples of this. Hold on. Here we go. All right. So if you remember the way the book's notation works, first of all, on the left-hand side, you have, of course, a definite integral. And that's because you're solving for a specific value. What you're really doing is you're looking for the area under a curve between two endpoints. Okay. Now, you may remember that capital F is defined as an integral or antiderivative. So if this is our function, the antiderivative, or integral as it's often called, is written in most books with a capital F. So in other words, you could have a statement like this. If you have an indefinite integral, which provides us with a family of solutions, so you find the antiderivative using the rules that we know, and then you have to add the c, of course. But if you have an definite integral, that means we need to solve for a specific value. And so we handle it a little differently. We're going to evaluate the antiderivative at both A and B and subtract one from the other. So that's what this is telling us. Okay, so we're going to evaluate the integral that we come up with twice, once at point B, once at point A, and then we'll subtract one from the other, and that will give us a specific value. Okay, so let's just make a quick, simple example. Suppose I'm interested in, let's say this is the right hand. This is y equals x squared, but we're only interested in the first quadrant here because we're looking for the points, let's say 1 and 2. We'll keep it really simple. And we need to know this area. All right, well, here's how do we do that? All right, first of all, it's x squared dx. Now, if you remember, we apply here the power rule. And normally we also have a c here, but because in this case we're dealing with a definite integral, we won't need the c. Instead, what we have is this. Now, the notation here, there's so many ways we could write this. A lot of books will write it like this: square brackets to indicate that we're going to evaluate this function at both endpoints and then subtract. That's what that is short for. But the other option would be to say, well, f of x, capital F, is x cubed over 3. Then if we evaluate that we're x equals 2, we have 8/3. Then we do the same thing for 1. And so we subtract. Oh, sorry. I just realized for a second there, I thought there was a 13 there. Let me fix this. No, that is not a 13. That's better. Okay, so then we just end up with 8/3 minus 1/3, which is 7/3. Okay, so that's what the fundamental theorem of calculus tells us. Now, getting back to this notation, what you often see is a lot of calculus books write it like this. And what they're telling you, this is a shorthand that says do this. Evaluate it at 2, for x equals 2, and then do the same for 1 and subtract. And again, I did it again. This should be, let's move this up here a little ways. There you go. Um, okay, so what you're seeing here is the fundamental theorem of calculus being used to find the area under this curve, y equals x squared, between 1 and 2. And that's our 7/3. Okay. I don't know. You know what? I turned something on by accident here. Let me just sort of get rid of it. Okay, that's better. Oh, but no, that didn't help at all. What is going on here? All right, I'll deal with this later. This is a new computer. That's why this is happening. All right, let's get back to it. Oh, okay. Well, that means there's some examples here. I mean, I guess we could try one more. Let's do this one just to get a little bit more practice. So, first things first, whenever you see something like this with a messy radical, probably your best bet is to write it as 3x to the 1/2 power. Okay. And then with an integral like this, we know that we can move the constant outside. That usually makes things a little bit easier for us. And now we can go ahead and apply the power rule for integrals, which means x to the 3/2 over 3/2 dx. Not dx, sorry. Hold on one second. I just realized I wrote this incorrectly. What I should have done is this. There we go. And just write the endpoints here. Okay, because now it's already been solved. There's no need to keep an integral sign there. And now what I would like to do is get rid of this pesky 3/2 down here. So I'm going to actually end up multiplying by 2/3. So I end up with 2x to the 3/2 evaluated between 1 and 4. And again, we can write this in a couple of different ways. Um, 4 to the 3/2 minus 1 to the 3/2. Well, that's easy because it's just 1. What is 4 to the 3/2 power? Just as an aside, remember that what you're actually doing here is taking the square root of 4 and then cubing the result. So that's equal to 2 cubed, which is 8. The other option was, of course, to go to your calculator. So you're going to end up with 2 times 8 minus 1, 2 times 7, which is 14. Okay. So I guess we could go to Symbolab and get a look at what this graph looks like. So yeah, so they're asking us to solve underneath this curve everywhere between 1 and 4, which should be basically here and here. All right, I guess, yeah, we don't need to do all the examples. That will suffice. All right, the mean value theorem for integrals. This is going to provide us with a very important result. And basically what it says is that if you look at, actually, let me copy this. Now remember, up to this point, every time we've had an integral, we're illustrating it with rectangles. And we saw that there's two different ways of using rectangles. Okay. We could have inscribed, where the area of the rectangles is too low. And we can have circumscribed where it's too high. Because it depends on which endpoint we choose in the rectangle to connect to that curve. But we also saw that as we take the limit, as the number of rectangles goes to infinity, the two of them will converge to each other and they'll give us the actual area underneath the curve. So what they're doing here is they're turning this into an average. You notice how we have C here, which is halfway between A and B. Here on the left, the rectangle is too big. On the right, it is too small, but somewhere in the middle, there exists a rectangle whose area matches perfectly with the curve. Okay, so we're going to find it like this. So you've got f of c, the midpoint, times b minus a is the same thing as the integral from f of x dx a to b. So let's see what their example is. Oh, okay. No, they're not going to give us an example yet. They're going to show us that we can use this result to come up with an average value for a function. Okay. So if a function is integrable, we always assume, there's always a lot of assumptions going on behind the scenes with all of these results. Here, the assumption is that the function itself has an integral. If it does, then the average value can be calculated very simply as you take the actual total area and divide by the difference between the two endpoints. And that is going to be the average value. Okay. So I think they do have an example for this one. By the way, don't forget, I guess this is going to be a constant problem in these slides. This L here is supposed to be the ellipsis three dots. I don't know how that happened, but I guess they never fixed it. Anyway, so what we're going to do, they're going to derive the result by defining delta x as b minus a over n, and then telling us that the area is equal to 1 over n times the sum of these rectangle heights. Okay, the heights of the rectangles. So in other words, let me try that one more time. All right, it's not great, but you can see what I'm doing. All right, so what they're saying is that the delta x, now here's A, here's B. Each one of these has the same width. These are not Riemann sums. These are all the rectangles are the same. N is the number of rectangles. And of course, each one of the C's that we're referring to here could be either the left endpoint, the right endpoint, or possibly the midpoint. So if we assume that it's the right endpoint here, each one of these, the height would be, all right, so this is actually rectangle number 1, 2, 3, 4, 5, 6, 7. So it would actually be C7. And each one of these, as you can see, has the same base, but a different height. So if I want to know the area, and given that they all have the same width or base, all I have to do is add up all the FCIs, and then I can just divide by the number of rectangles. Okay. Now they're calling this AN to indicate that N is the number, A is a function of the number of rectangles. Okay. So then what they want you to notice is that if we, let's see, what have we done? Oh, they multiply and divide by B. So algebraically, what they're trying to do is show you how this turns into this. So yeah, because what they're saying is I can rewrite this as, okay, that's my area. And what they're saying is that if you multiply by this ratio, which is just equal to 1, and then rearrange it a little, and those are constants, so we can move those anywhere we choose. Um, so what we're going to do is basically swap these two. But then by definition, that's just delta x. And then that's it. That's the average value of our function. But in the limit, as we allow n to go to infinity, we're going to wind up with 1 over b minus a. Okay, so that's where this is coming from. Okay, so this is the average value of that function over that interval. Okay, so here's an example. Great. So the function is 3x squared minus 2x. Okay, and so the average value, and the graph is right here, so I don't have to go look it up. This is what it looks like. And the endpoints are 1 and 4. 1, 1, and 4, 40. And now the average value, if C is the midpoint, no, it doesn't look like it's the midpoint. They've inscribed a rectangle. Well, I guess I didn't get it in the right spot. Look at that. Um, Oh, I see what they did. No, they waited. They didn't draw this until they'd solved for this. 16 is the height here. Okay. All right. That's why it isn't just some random location. Yeah, because it has to be like halfway, right about here, maybe. All right. It doesn't have to be just right. You can see it from here. I'm never going to get this right with my handwriting. Um, maybe about here. Okay. So the one on the left, actually, I've got color here. I might as well use it. So anyway, so obviously the rectangle on the left is inscribed, sorry, circumscribed because it's taller than the curve. And the one on the right is inscribed. And where they meet, that would be our average. Okay. So it's 16, but they want us to see why. So in other words, all they're doing is saying, listen, it's 1 over b minus a. The function is, of course, 3x squared minus 2x. And that's from a to b. So now, before we go any further, we might as well integrate 3x squared minus 2x. And, there's a couple of ways we could do this. We could rewrite it as 3x squared dx minus 2x dx. Apply the power rule. I'm not going to put in the c's because we're actually going to end up using this with a definite integral. Okay. So I end up with x cubed plus x squared. Oh, sorry, not plus, minus. Well, that was close. Okay. So in other words, what we're going to end up doing is this. This definite integral here, let's write it down one more time. 1 over b minus a times the integral here of 3x squared minus 2x from a to b, where a is 1 and b is 4, is, but now when we evaluate this, I'm sorry, not 3x squared, the result of x cubed minus x squared. Evaluated from 1 to 4. And so, as we saw earlier, well, 4 cubed minus 4 squared. And then from that, we subtract 1 cubed minus 1 squared. Okay. So we have 64 minus 16 minus 1 plus 1. And we end up with 1/3 of 48, which is 16. So the average value of the function in this interval is 16. And on this rectangle, that's why, because this ensures that the rectangle does cover that area in such a way that the left half is circumscribed and the right half is inscribed. Okay, so that is that. Now, the second fundamental theorem of calculus is we don't see it quite as often, but what they're telling us is that the definite integral can be, oh, sorry, this, it doesn't equal. It means that for this definite integral, the corresponding antiderivative can be written as, now if you notice all of a sudden these t's showed up out of nowhere. That's because one of our limits of integration is x. To avoid confusing everyone, we're going to use t. This is called a dummy variable. We only need to do this when one of the limits of integration is the variable x itself, because this x will get substituted into here, but we have to know we don't want to have two different x's because they mean two different things. Okay, so that's why it's written this way. Let's see, what do they want us to do here? This is a trig function, and what they would like us to do is basically figure out the area under this curve. So the antiderivative is cosine x because the original function was cosine x. So they're showing it to you down here, and the graph, at least over the interval they're interested in, looks like this. And so what they're doing here is they're saying, well, you know what we could do is we could create a series of rectangles and add up their areas. Like they said here, we could try 0, pi over 6, pi over 4, pi over 3, pi over 2, or what they are recommending that we do instead is this. So we start out here again. The integral, and if you remember that since the sine, which is the same thing as saying that the antiderivative is sine x plus c. Okay. Now here, because um, we're evaluating an area, we're going to use 0 up to x, which means we need the dummy variable t. And so they're going to have us evaluate it. And of course, we'll evaluate it at x and then at 0 and then subtract one from the other. So the sine of 0 is 0. You can confirm that on your calculator. Oops. Yeah, it's 0. So we end up with sine x And at the end, you can see the right endpoint x equals pi over 2. The area is simply 1 because I'll just confirm that real fast, but this is pi over 2 radians, which is the same as 90 degrees. And that would be 1. Yes. Okay. Oops. Now, if we were to take this and differentiate it, it would just bring us right back to the original function. That's what this is telling us. So in other words, if you apply a derivative to an integral, it just brings you back to the original derivative. That's really all it's saying. Okay. So here, what they're saying now, you notice again, they're using the dummies. Um, so what they want you to see is that based on this logic, we're going to just wind up with radical x. If that's f of t, then f of x is simply x squared plus 1. Okay. Net change. Um, so this is an interesting one. If we integrate, now when you take the derivative, if you notice they're using this notation, we start out with this function, capital F is the antiderivative, of course. So in other words, if I apply this operation, I'll end up here, plus the C, of course. And if I do this, well, from A to B, instead I evaluate it between those 2 points. But what they're saying here is that this is the same thing as saying, because when you take the derivative of the integral, it brings you back to the original function. Okay, that's what it is. So here's an easy example of this. So let's say, and again, it's a physics, they love their physics. Um, During 20 minutes, we got a tank here that's filling up with some chemical or other at a rate of 180 plus 3t liters per minute. Time, t, of course, is the time variable. And usually when you have a time variable like that, t equals 0 means right now at this point in time. So here, um, t is in minutes. T equals 0 means now. And then let's say t equals 60 means 60 minutes in the future. So they're going to define this function over the interval from 0 to 60. And then maybe the tank is full, or maybe the behavior changes somehow. But that's what this function looks like. So you basically have, oh, by the way, whenever there's a t variable, it is almost always going to represent the independent variable. In other words, it's taking the place of x. And so here's 0 and here's 60. Okay. Now, they want to know how full the tank is in 20 minutes. But first we have to define C of T is the amount of the chemical. Let's say, um, but the derivative is the rate at which the tank fills. It's kind of like we did a couple of examples where we had the motion of a particle, and then the first derivative was the velocity. So it's kind of the same thing. This represents the rate of change at which the tank is, the volume of a chemical is changing in the tank. So what they're going to tell us here is that that function that you're seeing there, although, yeah, they did tell us. All right. Because they told us that it fills, that means this is actually not C of T, it's C prime of T. Because that's the rate at which it's filling the tank, not how much there is at any given time, but how fast it's filling. Okay. So if that's the case, how much flows in after 20 minutes could be interpreted to mean the integral from 0 to 20 of 180 plus 3 dt. Now, of course, we know how to do this. And then we just evaluate it. Now, if you notice, when we evaluate at 0, all the terms will just drop out. So yeah, we don't have to worry about that. So we've got um, 180 times 20 is 3,600. Then we have 600, which mean and minus 0, 4,200. I guess that would be liters. All right. Now, this looks like it could be very useful in physics applications, but it's not even just physics applications. It could be used to describe, for example, how fast the balance in your bank account is growing or something like that. Okay. So there's a lot of potential uses for this kind of thing. Physics, here we go again. So they're integrating the velocity function, which you remember is the first derivative of the speed or location. And so what you basically have is the velocity over 2 points is the difference in the positions of the two particles. Um, Now here you have to watch it too, because if the curve of this function goes underneath the axis, that actually technically has a negative integral. And so if you add them up, you're going to have a problem. So what they're recommending you do here is take the absolute values, and then you'll have the actual distance that it traveled. Okay, remember we ran into this before. The if you're integrating a function underneath the horizontal axis, it gives you a negative result, which means that you can't really interpret it any longer as a distance. But if you take the absolute value, then that's not a problem. All right, here's an example. Velocity. Yeah, so Newton would be proud of this example. T cubed minus 10t squared plus 29t minus 20. Remember, the velocity is simply the derivative of the speed or location. Okay, so first, what is the displacement, or how far did it go over the interval 1 to 5? And then what's the total distance over that interval? So the first thing is going to require us to solve for the velocity. By the way, let me just, oh yeah, it's only defined over 1 to 5. I was going to say that that's kind of important. Oops, we don't forget that dt there. Now, of course, I'm using the power rule here. For example, the integral of t cubed. And normally there'd be a constant there, but we don't need it because here we're using it for a definite integral. Okay. So anyway, now we just substitute. So we do all the fives first, and then we'll do the ones. All right. So the first 5 to the fourth is 625. 5 cubed, 125. But then remember, we're multiplying it by 10. So that's 1250 over 3. Then we have, now here we have 29 times 25, 725 halves minus 100. Now, obviously, we're going to have to find a common denominator in there. And then in the denominator, we have 1/4. I just realized that I've got to be careful with these exponents. This is not 14, it's 1 to the fourth. All right. So, um, what we could do, I think we can choose a common denominator of 12. Let's try that. And then we'll do the same thing in the denominator. Okay, so what does that leave? It leaves us with a mess, but everything is divided by 12 at least. So in the first term, I'll just run through it real fast on my calculator. And 625 times 3. So that's the first term, and then we still have the second term to subtract, don't forget. Um, oh, I just realized this equal should have been a negative. All right, let's just get through this really quickly. — 174 over 12. So anyway, what does this leave us with? 25 twelfths minus whatever's here. Here I got minus 107 twelfths. And that one we can simplify it a little because they're both divisible by 2 at least. Well, what do you know? It's just 11. Okay. I wasn't expecting that. It's 11. All right. And so forgot what the oh, so that would be the so-called displacement. Oh, no, I must have made a typo in there somewhere. I've got 25 twelfths right, but the 10, what happened here? 107. It's 103. I know what I did wrong. I left out the 3 here. Well, that was stupid. All right, let me try that again. Minus 3, minus 40. No, but now I got 109. I must have done something else wrong. All right. Well, we don't want to waste too much time. The correct answer apparently is 103. All right. So I'm sure there's a small mistake in there somewhere, but we ended up with 32 thirds feet. Okay. And then I think there's one more part to this. Then they want the distance, which now what they're doing here is they're using absolute value, but what they're pointing out here is that if you look at the curve is above the horizontal axis from 1 to 4, but below from 4 to 5. So what they have to do to make sure we get all positive values is when we get to 4 to 5, we make it negative. Okay. And then you can see after all the dust settles that we have 71 feet. So that's the tricky part right there. We can't integrate over the entire interval because of this negative portion of the curve. So instead, we have to look at the curve and find out where it becomes negative, and then in effect, take the absolute value of that region. All right. So I think that's 4-4. Now, 4-5. Now, this is the one where it becomes less theoretical and more directly relevant because we're going to use this technique on a regular basis. Um, In fact, sometimes you may have heard of this referred to as U substitution, and it's an awfully, awfully powerful technique. So it comes from the chain rule, as a matter of fact, but this one we really want to spend as much time as we can because we're going to see it on a regular basis. And once we've done a few more of these, once you get the hang of it, you'll be fine. But we do need to get some practice. Okay. So that's it. Now, once that's done, like I said, at long last, we can start the new content, chapter 7, which is applications of integration, of course. So I think maybe we'll stop. I don't want to rush through this part. This is awfully, awfully important. And yes, it is directly taken from the chain rule. But so this is 4-5. And once we're done with this, we can start the new material. Now, if you remember, I also deliberately made all of the WebAssign due dates start on the 14th because, if I remember correctly, because we would not have gotten enough material done by then. And as a matter of fact, I might even have to postpone that a little bit. We'll play that part by ear. So we'll see how it goes. But for now, we'll stop here. And then when we meet again, we'll do 4.5. Okay. So I'll see you then.